Hi, this is Seth Wilson with the Tektronix AWG sampling head team, and this is the command line interface testing video. I'd just like to start with a little background on the code before I start the demonstration. So first, we just check that the user has input the correct usage for the CLI. All that the user inputs is just the calibrate as a function, and then the frequency of the waveform that they want to calibrate, and then the function continues, and after that's input, the function asks for the user to configure the AWG at the frequency that they input above, and press yes to continue and begin waveform capture. Down here we start a timer to make sure that we're within time, and then here we calculate the number of samples that we will need based on our fractional n sampling method. This function also calculates the equivalent sampling rate given our AWG frequency and the sampling rate of our clock, which is constant at 10,000 megahertz, or 10 megahertz rather, plus 1 hertz. And the amount of time the waveform capture will take is calculated as well, based on the sampling rate and the number of samples required to capture the waveform. And then that time is simulated here by sleeping the thread, because we're, again, just using sine wave simulated data with a callback function here. In reality, this callback function will be used on a function that Dylan writes, and that callback will be used asynchronously. As you can see, the class is asynchronous in order to collect the samples and then process them. And so, yeah, let's begin the demonstration. So here's the demonstration. The command is calibrate, and the input frequency of the AWG is 500 megahertz. That's our maximum. And so we press enter, and it asks us, the user, to configure the output waveform with the frequency specified. So at this point, the user would just get up and essentially program the AWG however they would want it, just as long as it meets the frequency that they specified. And we press yes to continue, and enter. And then here, the timer has spit out our time to complete the waveform capture, and now the data is passed to MATLAB for processing, where it will create some plots for us. It just takes a little while because of the amount of samples that are required. And here we go. So we have our 3 plots that we want. SFDR, which shows our spur at 97.37 dB at the correct frequency. It's just difficult to see because of how high of frequencies we're working with, but that's correct. Similarly with the FFT, and I'll just zoom in to show you. The reason these are just very fine is because the number of samples is very high. And so you can see our 2 tones, or 1 frequency tone at 500 megahertz rather, and a 500 megahertz tone and time domain. So for our interface properties, we should be meeting our outside to command line interface user in properties of user inputs the frequency of the AWG waveform. As you can see, that's what happened in the first place. The waveform capture happened in less than 20 seconds, and that's confirmed with our timer and our calculation based on our fractional n method. The user interface is text-based, And then finally, the CLI informs the user when to begin output of the AWG, and capture begins when the user inputs Y. So all of those were met in this demonstration and should be on the real thing. And for the output, our properties were performs DFT, which it does, graphs both the time domain and frequency domain, that was done, and then finally we wanted to graph SFDR, which we did as well, and final as well. The last one is spit that number out into the CLI for final results. So that's it for our testing, and we'll see you in the demonstration. Thanks.